Well, welcome to the second of Lewis Bowen's Minerva lectures. I mean, it's a mini course. The title of this talk is L2 invariants and Benjamini-Schramm convergence. And I see that some people might not have been here last time, so you might review what you're doing. You're giving 5 lectures, and they more or less, so maybe it's the same topic, but does each one require the last lecture?
No, not at all.
Okay, so thanks.
Okay, thanks. Yeah, as always, it's an honor to be giving these talks, and please ask questions. I like that. So as Peter said, the theme of these talks is Benjamini-Schramm convergence, which is a way that a sequence of finite graphs can converge to a random rooted graph, or you can replace graphs with manifolds or simplicial complexes. And so what I intend to do for this lecture is to give an example of how it can be used to solve a problem in geometry, which is very much related to spectral theory. Okay, so I'm going to start by explaining what the problem is. And, okay, so it has to do with Cheeger constants. At least this is the way that I started thinking about it. Okay, so X here will just be a, just a Riemannian manifold. Okay, so the Cheeger constant is the following infimum. We consider all compact submanifolds.
Come stand next to me. This is the standing area.
So we consider all compact submanifolds which have a volume at most half the volume of X. And we consider this isoparametric ratio and take the infimum. Okay, so for example, the Cheeger constants, so in most of the talk I'm going to be interested in infinite volume manifolds. So this condition is just vacuous. So for Euclidean space, the Cheeger constant is just 0, because you can take a very large ball and the volume is growing like radius to the n, and the area is growing like radius to the n minus 1. But the Cheeger constant of hyperbolic n space is positive. Now this is a really crucial difference because, for example, it's an important difference for ergodic theoretic arguments. The reason why is because what this means is that if we have some kind of process or random process, for example, that we can kind of approximate Euclidean space by a large but finite or compact subset. But with hyperbolic space, we can't do that. The surface boundary conditions are non-negligible. Okay, so I was interested in the following problem. And it can be generalized a great deal. But in any case, I'd like to understand what's the infimum of the Cheeger constants for hyperbolic n space mod gamma, where gamma is something in the isometry group. It's a subgroup. And I'm always going to require that this is a manifold rather than some, orbifold or something, and that that this map is a covering map. So it's just to say that the group is acting properly, discontinuously, and freely. Okay, and here I'm also going to make one more requirement, that gamma is free. So it's a free group. Okay, what can we say about this? Is it 0 or is it positive? So I'm interested in free groups because we understand them fairly a lot. Their structure is very transparent. And so if this turns out to be 0, then it's kind of like, well, we can approximate hyperbolic n space by a large tree that's kind of thickened and hope to be able to push arguments about free groups forward to arguments about hyperbolic n space. That was my original motivation. So let me just kill you. There's some other good motivations for this, but I'll get to that in a moment. Okay, when the dimension is 2, you can find pairs of pans. So this is H2 modulo some free group of rank 2. With the property that, well, you'll have 3 simple closed curves here, and you can make these closed curves of any length that you wish. The interior will always have volume pi, or area pi. And so it's easy to see that you can get this down to 0. So the answer is just 0. For n equals 3,
put a condition that the injectivity radius, that if this happens only if the injectivity radius goes to 0, right? That's but probably that's.
I suppose so. So, you know, I don't think it's not just a matter of injectivity radius. Now that you mention it, it is.
With gamma, you care that it's free. It's like surface groups, of course, you can construct a lot of, big injectivity.
You can, right.
So then it's going to be 0. That's it.
Yeah, here it's also going to be 0. Right, the answer.
So even
Because right here you can find you can find finite volume 3 manifolds which fiber over a surface, and the fiber is going to, well, if you look at H3 modulo the fiber is going to be a free group, or I should say pi 1 of the fiber. What it looks like, roughly speaking, is something like a surface with a puncture times r. And so you can just find a very large, you can take a kind of surface times a large interval, and you'll get that the boundary is going to be bounded. The area of the boundary will be bounded by like some constant depending on the genus of the fiber, but you can get the volume to go to infinity. Okay, so this is, well, I got stuck on n equals 4. So what do you do? I mean, this is already a non-trivial. For n equals 3, the answer, you know, already requires some non-trivial results. Okay, so I'm not going to. I will answer this later on in the talk, but not right now. I want to have a little bit more motivation. Explain why this is an interesting question.
Whole finitely generated.
Yeah, let's say finitely generated. Yeah. Okay, so we could be interested in lambda 0. This is the bottom of the spectrum of the Laplacian. You could also define it by a variational principle. So it's known that lambda 0, let's see, make sure that I get my constants correctly. This is forms a lower bound for the Cheeger constant. So this is due to Cheeger. And you also get an upper bound due to Buser. So these are positive constants that depend on the dimension and on a lower bound for the Ricci curvature.
Lambda 1 or?
Did I?
It's lambda 0.
No.
Lambda 0. Because this is an infinite volume. So rather than a... Okay, and then the lambda 0 is, well, in the presence of geometrical finiteness, there's a formula that relates lambda 0 directly to the Hausdorff dimension of the limit set, if you're interested in groups acting on hyperbolic n space. So,
The other way, or is there some reason that it's this way? Lambda is bigger than this.
did I make a, I'm sorry.
So this, in the case of compact surfaces, should be our usual lambda 1.
No.
No,
Yeah,
it's
it would be the
different.
analog. I think
It's different.
Cheeger's lambda is bigger than. But anyway, they both go to 0 together. That's clear.
Yeah.
Not the rest wrong.
Oh, I've got some.
I think you got lambda 0. Marian's right.
Oh, yeah, sorry. I am backwards, right? Yeah. You're right, I'm sorry.
But they both go to 0 together. That's all you.
That's all that I'm going to use. Thank you. Okay, yeah, lambda 0 also, as lambda 0 goes to 0, the Hausdorff dimension of the limit set goes to the full.
The thing you should remember is Cheeger put a lower bound for the eigenvalue,
Okay,
not an upper bound.
yes. Okay. So there's a result of Phillips and Sarnak. So they were interested in the in lambda 0 of Hn minus modulo gamma, where gamma is a Schottky group, which is a special kind of free group acting by isometries. And they showed that this infimum is positive when n is at least 4. Okay, and when n equals 3, this was also handled by Doyle.
Not also handy.
I'm sorry.
We didn't do that.
Yeah. This was handled by Doyle, and yeah. Okay, so this is just one motivation. Another motivation is that, well, there's this well-known open problem. Do you have a closed hyperbolic M manifold, or finite volume, 4 manifold, which fibers over a surface? So does there exist one? With fibers being surfaces. So the point is that if there is one, then the fiber is some group that acts by isometries on hyperbolic force space, and it's a surface group, but that's basically like a free group, so let's just ignore that point. If we were to perturb it a little bit, we might imagine that we could keep it geometrically finite, and that the limit set would remain close to full. So maybe I should say this, say it again. Pi 1 of the fiber is some subgroup of the isometry group, and you can prove that the limit set of this has to be the entire sphere at infinity. It's the entire boundary. And so one might imagine that maybe it's possible to perturb this fiber and make it geometrically finite and keep the Hausdorff dimension of the limit set very close to 3. And that would mean that lambda 0 would be very, very small, and the Cheeger constant would be very small. Okay. So yeah, other questions or comments?
Do you have to say that's classical?
For these Schottky groups, yeah, I think so. These have to be round, yes. Classical Schottky.
Also.
Yeah, there's, okay. Okay, so, so my theorem is that in the case n equals 4, the answer is that this infimum is positive. So there is a definite lower bound on the infimum of the Cheeger constants, and therefore also on lambda 0, and there's a non-trivial upper bound on the Hausdorff dimension of the limit sets.
It's sort of a quantification of Mostad, because Mostad's theorem says you can't be, the group can't be free if you are a lattice in hyperbolic four space.
Yeah.
And this is a statement which quantifies it. It says if you're free this in something quantitative, it's a much stronger statement. That's the way I would view it.
Okay. Yeah, okay. So the proof is really, it employs a soft argument. So it doesn't actually use much of the detail of the setup. It's homological in nature. What we're really using is that hyperbolic four space has a positive L2 Betty number in dimension 2. So you have non-constant or non-zero harmonic L2 form, two forms, L2 two forms. And on the other hand, if gamma is a free group, for example, then all of its higher homology groups, in dimensions 2 and higher vanish. And that's the relevant information. So you could actually replace free here by a surface or pi1 of a three-manifold group. It doesn't actually matter. So it could be, for example. Okay.
Do we have geometrically finite condition?
No, it's not required. No, there's no geometrical finiteness assumption either.
And it's only for 4?
Well, it works for even dimensions,
The fact that
at least 4.
0 cannot be geometrically finite. I mean, for n equals.
Yeah, well, I mean, presumably this infimum could be realized. I mean, might not be realized, might not be attained, but you would still have, if the infimum could be 0. But no, there's no geometrical finiteness assumptions here at all. That's not the issue.
Reasonable lower bound?
Unfortunately, no. I don't know any lower bound precisely. It seems like one should be able to find one, but I don't know. I haven't tried. Okay, so let's see. There is. Perhaps I should give the general answer. With the general theorem. Yeah.
General conjecture says that for all n above 4, right?
Right, yeah, I don't know what happens when n equals 5, for example. I have no idea. It seems like it should still be positive in all higher dimensions, but the techniques don't work because all of the L2 Betty numbers vanish in odd dimensions. So, so I'm actually not quite sure. Well, okay, so I'll give you the general theorem. So here's a definition. If I have a group gamma, so this is just some group, I can define, this is kind of an ad hoc definition, but that suits our purpose. We look at Betty numbers in dimension D of subgroups of finite index and we normalize by the index and take an infimum. And let's see, right, okay. So for free groups, for example, this is just going to be 0 for, in dimensions 2 and higher. Okay, so I'll let GD be the class of all groups such that gamma is residually finite. And I want to make sure that I'm doing this right. Okay, and if we take any subgroup, then its lower asymptotic Betti number in dimension D vanishes. Okay, so we could go over here and look at.
You didn't put Benjamini, yeah, equals 0.
Yes. Okay, well this one's going to, this will be the conclusion. Okay, so the theorem is going to be that this infimum is positive if, okay, X is a smooth, contractible Riemannian manifold. And we require that it's L2 Betti number, so we require, let's say, the existence of a residually finite uniform lattice or co-compact lattice with positive L2 Betti number in dimension D. Okay, so my point of just putting all of this down is just to say that, there's very little that's used about hyperbolic space or about free groups in general. It's really a homological statement. Any?
Of course, these things are almost impossible to compute except for the whole space. An L2 Betti number, I once, I think when I first moved to Gromov, I said, L2 Betti number, he said, transcendental garbage. Written many papers on it. So I guess you were telling me you couldn't compute anything. The only case really you can compute it in hyperbolic end space, right?
Symmetric spaces, sure,
Oh,
more generally.
Okay.
Yeah, people have been working on buildings,
But mainly the kind of look theory just gives you an equivalence, but at the top you have to be able to compute it to say something eventually.
Sure, yeah. There's still a lot of open problems, of course. Right. It's like for aspherical manifolds.
It sounds easy, but is there an L2 harmonic D form?
Yeah.
Non-zero, that's the question, and it's awfully tough.
Yeah. Right. Yeah. Okay. Okay, so I will now explain the key idea, which uses Benjamini-Schramm convergence. So I'll remind you what that is. And this time in a different setting than what we saw in the previous lecture. Okay, so I'll have a sequence of simplicial complexes. So these are finite connected simplicial complexes. With a degree bound. So all of the vertices have degree at most d. Okay, so we'll say that this Benjamini-Schramm converges. If the following is true, I mean, maybe I should just say that the intuition is that they should be converging in some local sense, but it's not just local, it's also probabilistic. So the idea is that if we choose a vertex in Ki uniformly at random, and then we look inside a ball of radius r, we see some finite simplicial complex. The distribution of that finite simplicial complex should converge.
So a ball, so every edge has length 1?
Yeah.
Okay.
Okay. So, but then you want to talk about the limit object sometimes. In this case, it's not actually too important. Well, I guess it is going to be important for us. So let's say it this way. Let's say there exists a random rooted simplicial complex. Such that okay, well, we take the law, so, right. So if we choose a vertex uniformly at random, then we consider the distribution of the ball of radius r, where r is just some parameter. This should converge as I tends to infinity to the distribution of the ball of radius r centered at the root vertex of our random rooted graph.
Complex.
Yes, random rooted complex, yes. Last time it was a graph. Yeah, so, you know, I mean, some easy examples that we saw last time is that Z mod NZ, the usual Cayley graph for Z mod NZ, Benjamini-Schramm converges to the usual Cayley graph for Z, for example. Another case is that if you have, let's say that X is a simplicial complex, and let's say that gamma acts on X co-compactly and freely, then we can look at X mod gamma. And let's suppose that we also have, right. Let's suppose that we also have some normal subgroups that are finite index. And decrease to the identity. Then you can look at these covering spaces. These will Benjamini-Schramm converge to X itself in a natural sense. I mean, X is not exactly a random rooted complex, but you know, you think, yeah.
Your examples don't have the random feature.
Yeah, this is an example that doesn't really have the, you know, if the limit object is vertex transitive, so that the automorphism group of the complex acts transitively on the vertices, you don't really, you know, randomness isn't necessary.
Can I ask a question with this theorem about so when you define GD, you had all these gamma prime
where the Betty number was 0. But then you also require the existence of something with positive Betty number. So can you comment on how, for a fixed symmetric space, how the Betty number depends on the choice of group?
Well, okay, so for a symmetric space, or any X really, if you have a lattice with positive L2 Betty number, then all of the lattices have positive L2 Betty number. And in fact, they're just, they're related to each other by covolume. So it makes sense. So the L2 Betty number of lambda divided by its covolume is a constant that it doesn't depend on lambda.
You can compute this. If you take a finite index, then you can still see if you have an L2 harmonic.
Sure, I was just surprised because then then the gamma you're considering are infinite covolume.
Right.
So you somehow expect there's more room for harmonic length forms. But even though the co-compact guys have, it just seemed contrary to my intuition that the co-compact guys would have positive Betty numbers, and then the much bigger objects would have 0 Betty numbers.
Oh, I see what you mean. Yeah. This L2 Betty number is a kind of asymptotic object.
But they sort of get bigger under covers.
Yeah.
I would have expected bigger objects to have bigger L's.
Yeah. The theorem that I'm about to tell you might help with your intuition, actually, with this. Yeah, okay, so I guess I could put it here. So, this is the kind of key lemma that makes everything work, is the following. So if we have a sequence of finite simplicial complexes that are Benjamini-Schramm convergent, then the following limit exists. We just take the ordinary Betty number in dimension D, and we normalize by the number of vertices. That's it. What this is, I mean, one can interpret this as in terms of L2 Betty numbers of the random rooted complex. So, right, yeah, secretly, right, this is the L2 Betty number of the random rooted complex that it limits on. Okay.
So that Betty number is deterministic, even though the graph is random?
Well, I didn't define what this means. I'm really taking an expected value here. It's, but in the case that we're going to apply it to, K infinity is really hyperbolic n space. So that's. So this theorem, the techniques go back to Luke. Luke was looking at he was looking at this special case, which I mentioned before, where you have some simplicial complex X and a group which is acting co-compactly and freely. So under these assumptions, Luke proved this theorem in, I think, 95, and Alec proved this generalization, I think it was 2009. Yeah.
Luke's not about Benjamini-Schramm, right? Or is it?
No, I mean, his original statement was not.
Just that the thing converges to kind of forget what there used to be a word for this kind of convergence, when you locally converge to it. Locally, you more like some space.
Right, yeah, exactly. That's the.
Radii of your manifolds go to infinity.
Yeah.
And they're all locally quotients of the same number. That would be.
Yeah, it's the same, right. Yeah, I mean, yeah, it's a bit more restrictive what Luke was doing, but I had to mention his name because really a lot of the ideas for the proof of this were already present in his work. Okay, so, yeah. Right, I thought I would maybe say a few more words about this at the end, but I'd like to sketch the proof of the main theorem first.
Sorry, I just walked in. What happens here with you're doing isometries of H2?
Oh, in this theorem?
Yeah, why does it not apply? And obviously you can have Riemann surfaces.
Oh,
Riemann surfaces are arbitrarily small. Cheeger concept.
they are not in, their one-dimensional homology does not vanish, even asymptotically, even when you normalize and take limits and so on.
Right.
Okay. So one step is to generalize this theorem of Ellick from simplicial complexes to Riemannian manifolds. And so that's, I kind of hesitate to write it all down because there's a lot of technical detail. But essentially you can you know, yeah, okay, so let me just say a few things. Let's suppose that we have, so suppose we have manifolds which are in, so let's say, hyperbolic 4-space mod gamma I, where gamma I is some group acting by isometries. And suppose these are compact. So first of all, if we take a point uniformly at random according to the volume measure, so uniformly at random.
What should we think are the dimensions of the MI?
4. Yeah.
So contained in, so these are what?
These are submanifolds. So I want to think of these as like Cheeger sets, like sets with relatively small boundary. That's how we're going to apply it. Okay. Right, okay. So you know, this is just a specific example, but one can generalize this a great deal. So I want to explain what Benjamini-Schramm convergence means in this setting. So I want to say that, okay, so suppose these are compact, and I got ahead of myself. I want to say that these MIs are converging to hyperbolic 4-space in this Benjamini-Schramm sense, if the following is true. We let VI be a uniformly at random point, and we consider the bowl of radius r centered at VI in this submanifold. And we're interested in what happened, when is this isometric to a ball of radius r in hyperbolic 4-space? Centered at some point, doesn't actually matter what point. We would like the probability that this occurs to 10 to 1 for all r. Okay, so if you unpack all of the definitions, this is what Benjamini-Schramm convergence means in this particular case. But you can already see that Benjamini-Schramm convergence is not going to be enough for the normalized Betty numbers to converge. Because you can kind of mess things up on a local scale, on a very small scale. You can have, you know, some manifold, and then you could just add, you know, a whole bunch of little tiny loops here or something, and that would just destroy whatever homological computations you make. So you need to have some kind of assumption that says that the local geometry is very simple and no complexity. So a theorem that can be generalized a great deal says something like, if the MIs Benjamini-Schramm converge to, say, hyperbolic force space, and, well, we need bounds on, well, let's say, and small enough balls are strongly convex. Strongly convex means that between any 2 points there's a unique midpoint. So, I should say there exists an epsilon such that balls of radius less than epsilon in MI are strongly convex and have a volume bound. Volume at least, I don't know, delta, which is something that's positive. Okay.
Balls of radius less than or equal to epsilon?
Oh, yeah, I didn't say this correctly, you're right. And the volume of a ball of radius epsilon in MI centered at any point should be at least some number positive. So there has to exist an epsilon and a v naught, and these have to be positive numbers. Okay, then the normalized Betti numbers converge. So we just look at the ordinary Betti numbers and divide by the volume and take the limit. This exists. And in fact, it's going to be some, well, yeah, I mean, it'll have something to do with the L2 Betti number of hyperbolic force space, the L2 Betti numbers. But it's not exactly clear what exactly it will be, because we've normalized in a way that makes it unclear.
With a zero knot is.
I'm sorry?
With a zero knot is.
Yeah. Well, whether it's zero or not, though, is not going to depend.
Part of the point is that MIs would be infinite volume.
No. These are finite volume.
Finite volume, but they're also, but they're not hyperbolic. But there are some complexes.
Oh, I'm assuming that they sit inside hyperbolic force space modulo gamma I for some gamma. So they're subsets of hyperbolic manifolds. Yeah. Okay, so I'll give you the kind of fantasy proof of the main theorem. This talk is kind of weird. I will. Okay, the fantasy proof of the main theorem. So we'll assume that we have some sequence of subgroups of the isometry group with Cheeger constants of the, well, X here is hyperbolic force space, with and the Cheeger constants of the quotients tend to 0. So then what we want to prove is that these gamma i's have to have, well, they have to be homologically complicated in dimension 2, because H4 is homologically complicated in dimension 2. That's going to be the goal. Okay, so the idea is that we let Mi be a subset, a compact submanifold with area to volume ratio tending down to 0. Okay, we would like to claim, so we'll have to assume it because it doesn't have to be true. We would like to believe that these MIs are Benjamini-Schramm converging to hyperbolic force space. Then we can use the previous results to say that their normalized Betty numbers converge. And one other thing that we don't actually know is we don't really have good control over the homology yet. So we would like to say that maybe MI are, I don't know, homotopically equivalent to this quotient. Again, this is really doesn't have to be true. This can fail very badly. But if we assume that, this is just the fantasy proof, so. Okay, so if we just assume that these two things hold, then you can see how the rest of it goes. The normalized Betty numbers have to converge to, they do have to converge to the L2 Betty number of hyperbolic force space. And so in particular, these things have to be positive in dimension 2. And and since, okay, this is true by number 1, and by number 2, we can replace this with we can replace Mi here with the Betty number of gamma I.
Now that's just a group theoretic. Is the bottom now the index or something?
I'm still, yeah.
I mean the volume, okay, keep going.
Yeah, it's still the...
It's still the volume, all right.
It's still the volume, you're right. Okay. Okay, so about 1. So we'll fix both of these problems. So about 1. Well, there are two.
To get the contradiction, if gamma I are free, say, you would need to know that. So this is going to something non-zero. Oh, if you free, then the second homology. Okay, just 0.
Right, yes. So this is, right. So if we're free, then this is going to be 0, so it can't hold for free groups. Okay, so about number 1, there are two ways that this can fail to occur. One is that it might be that when you take a uniformly random point in M sub I, that it's close to the boundary for some reason. And so when you look in its radius R neighborhood, you're getting points that are in the boundary, and that's awful. So what can happen, another way of phrasing this is to say, you have your manifold. Although the boundary has small area, it could have very long hairs that kind of come out. And so that when you take the radius R neighborhood of the boundary, it could have huge volume. So Buser actually studied this problem while he was proving this inequality relating the Cheeger constant and lambda 0. And so he proved that you can kind of chop off all of these hairs in a very nice way. Okay. So I won't, well, what he proved is that you can choose Mi so that if we take the radius R neighborhood of the boundary, take the volume of that, normalize, this is still tending to 0. And it's just a matter of, cutting off hairs, if you will. Okay, for the sake of time, I won't say too much. Okay, but there's still a problem, which is that
Is area bounded by the volume tends to 0
yes,
not MI?
this is MI.
Yeah. So this condition is used in the
This condition is used to get this. This MI is not the same MI. We have to change, we have to smooth things out, cut off some hairs. So these will not be like perfect Cheeger constants, Cheeger sets. They won't necessarily, realize the infimum, but they don't have to for our purposes. Okay, so there's one other way that this sequence can fail to Benjamini-Schramm converge, and that's if you have homotopically short loops in the manifold. But we can get rid of these by passing to finite index covers. So we just take, we replace our gamma I with a subgroup, and then with a finite index of subgroup of that one, as it turns out. We can get rid of homotopically short loops. So using, again, residual finiteness, we can remove homotopically non-trivial short loops. Okay. So after this is done, so we've replaced gamma I now with a subgroup of itself. But after this is done, we now have that these M sub i's Benjamini-Schramm converge to hyperbolic force space. Okay, we still have this problem that, well, it certainly doesn't have to be homotopically equivalent to the quotient, but we only need to get a bound. We do have this. This is still true. We only need to get an upper bound on the Betty number, and we get that from Meyer-Vietoris. So the Meyer-Vietoris sequence will imply that this is bounded from above by the usual Betty numbers here and also the Betty numbers of the boundary. Now the boundary, I guess it might be complicated, but it has small area. And if we take the radius R neighborhood for any R, that still has small volume relative to the whole. So when we divide by the volume of M sub I, this last chunk is just going to go away.
You're giving some universal upper bound for the Betty number in terms of volume, I guess, with the general setting.
Yeah, what we do, right, well, how it's done is that you take the boundary and you cover it by balls of a certain radius where you know that there's nothing topological happening in those balls. And then it's just a matter of, well, how many balls do you need? And you get a bound on the Betty number using that. Okay. So I guess, are there any questions? I haven't gotten as far as I had hoped, but that's okay. Okay, so I guess in the last 5 minutes I can say something. Yeah, I mean this is the theorem. That's the sketch. But I thought maybe in the last 5 minutes I'd say a related result. This is a theorem that's due to 7 authors. I'm not going to write down all their names because of time.
7 samurai.
Yeah, the 7 samurai. So this is Aber, Bergeron, Berenger, Galander, Nikolov, Rambaud, and Same. So I might have mispronounced his name. Okay, so G is a simple higher rank Lie group. So
What if the effect is correct? It goes down rapidly with the number of authors. You'd have to check that they actually, that this guy passed the baton when the other guy picked it up.
So gamma I in G is these are co-compact lattices, and we assume that the injectivity radius is uniformly bounded from below. And we assume that the volumes, or the co-volumes, tend to infinity. Okay, these are the hypotheses. What we end up with is that the limit of the Betti numbers, X here is just the symmetric space associated with G. The Betti numbers of the quotients normalized by volume converge to the L2 Betti number, or L2 Betti numbers of X. So for example, when X is, or when G is SLNR, or N is at least 3, these all vanish. So we know.
Those are the one case of building things we can compute. That's Alexander's work. Yeah.
Well, when X is hyperbolic space, well, this doesn't actually apply for hyperbolic space because we need real rank at least 2. Well, the real trick here is simply to show that these X mod gamma I's have to be Benjamini-Schramm converging to X itself. That's the main difficulty.
This is the case where the injectivity radius is not going to infinity, so then you really do need most of the manifold is looking, right?
Yeah, right. Well, we're not assuming that.
No, but they're not going to 0. Okay, but you could have manifolds which the injectivity radius doesn't go to infinity.
Yeah.
And it's still Benjamini. The volume goes to infinity, but this says as long as the radius, the injectivity radii aren't shrinking,
Yeah.
you automatically volume going to infinity means Benjamini-Schramm convergence, which is quite striking.
Yeah, that's right. Yeah.
Right? Correct. Oh, yeah. It uses lots of rigidity. Yeah.
That
Not
theorem, I mean, compared to this theorem, I mean, you don't have boundary here, right?
Yeah. Here you don't have boundary. Yeah.
Can you just like somehow?
Well, okay. The difficulty here is that we're not assuming Benjamini-Schramm convergence. We have to prove it. And here, I mean, we're also not assuming Benjamini-Schramm convergence, but we're using the Cheeger constant in order to prove Benjamini-Schramm convergence. That we have that we have something that's Benjamini-Schramm converging to X. Here, what we use is higher rank to prove that this has to be Benjamini-Schramm converging to X. So I'm almost out of time, so I'll just say it very quickly. This comes from the reason why is due to a theorem of Stuck and Zimmer. They basically classified all Benjamini-Schramm limits that there can possibly be, and they showed that, well, it either has to be a lattice or it has to be trivial, and you can rule out being a lattice. It can't be a lattice. Why? Well, this cannot be Benjamini-Schramm converging to a lattice. Well, that's because if that were so, what would have to be happening, you'd have to see something that looks like a deformed copy maybe, but only slightly deformed copy of the limit manifold. You'd have to see many, many copies of it. So these are all, slightly deformed copies of the limit manifold. And then these would have to be connected somehow by like little tubes. This is what X mod gamma I would have to look like for large enough I in order to be Benjamini-Schramm converging to this one. But that can't happen simply because of property T. Property T tells you that your lambda 1 this time has to be bounded from below by a positive constant, or the Cheeger constant has to be bounded from below. And this, and that's a contradiction because, the Cheeger constant here is very small. Yeah. Okay. I guess that's all. Yeah.
I guess we have time for a couple of questions. And as I said last time, Lewis is here for the whole term, so if you don't feel like asking him now, you can call him at any stage as he enters the room. But now would be a good time if there's a question.
Yeah.
So the thing that you mentioned that there's a classification for all the Benjamini-Schramm things, that's for higher rank.
Yes. Yeah. Yeah, it's a
higher rank.
it's a generalization of Margulis's normal subgroup theorem. You can see that it implies Margulis's normal subgroup theorem for one thing.
They have some theorems in rank 1 as well, but then I think you have to put some more hypotheses.
You basically have to assume that it's Benjamini-Schramm converging to X. So
I think the thing that's kind of surprising is that Benjamini-Schramm convergence is quite common. It's much more common than you might think. It's sort of hard not to be Benjamini-Schramm.
Right. Yeah. Well, one also, for me at least, what I found very surprising was that the Betty numbers are behaving in a continuous manner under Benjamini-Schramm convergence, the normalized Betty numbers.
The general audience, why Benjamini and Schramm introduced this?
Oh, yeah. So they, the results that they proved in their first paper on this showed that if you have a sequence of finite planar graphs, which Benjamini-Schramm converges, and moreover, you need one extra hypothesis, which they didn't like, but you needed to know that you have a degree bound on these finite graphs. Under that assumption, the random rooted graph that you converge to is some planar graph, and they proved that that's recurrent almost surely for simple random walk. So simple random walk is going to come back to its starting point almost surely. This was a little bit disappointing because they were very interested in the uniform infinite planar triangulation. What this is you take a sphere, you take the usual two-dimensional sphere, and you consider triangulating it with n triangles, where you allow all triangles, all triangulations uniformly at random. You pick one uniformly at random. Then what Omer Angel and Oda Schramm showed is that Benjamini-Schramm converges to a very nice object that they call the uniform infinite planar triangulation. So it's a random triangulation of the plane. And it's a model for two-dimensional quantum geometry, and it's well studied by probabilists. But they wanted to prove that that object is recurrent. They couldn't do it because they needed this degree bound. And when you take a random triangulation of the two-sphere, there's no degree bound at all. But as it turns out, the distribution of the degrees has an exponential tail. And it was just recently proven, like in the last 2 years, by Nachmias and Gurel-Gurevich, that with an exponential tail, the limit, exponential tail is sufficient to prove that the limit is in fact recurrent almost surely. So UIPT is recurrent. Anyway, it's a very different motivation, but it's another instance of Benjamini-Schramm convergence.